Hey students, so I told some of you in office hours today about this. So I came into my office today, right? I'm coming in, I'm going to film and do office hours and that kind of thing. And the light was knocked over. So let's see if you can actually see this. So I came in and the lamp, I can't get my, here we go. Can you see that? The light, it's like knocked over. What's going on here? I came in and that thing was knocked over and broken. The whole base is broken. So I'm sure you don't really care, but I just find it bizarre that it happened. I have no idea. During the middle of coronavirus, someone came in my office and broke my lamp. So the lighting, I think, is a little bit weird now. Let's see if I can just balance this thing. Oh, I guess if I lean it, I'm leaning against the wall now, so it's actually standing up straight. Anyways, that was what happened today. So let's return to our discussion of permutations. And let me think here. I think we left off with the recognition that you can take a permutation and break it up into, or decompose is the word we use. Decompose it into a product of disjoint cycles. So there's one way to represent a permutation. Another way is a product of transpositions. And the representation as a product of disjoint cycles, that's unique up to ordering. But decomposition into product of transpositions is definitely not unique. But, okay, and so that leads us to our next theorem. So this will be theorem 9.3. It seems maybe unfortunate that there's not a unique way to express your permutation as a product of transpositions, but that's how it goes. And so what we're about to show is that there is something unique about that decomposition. So let's let sigma be an element of Sn. So we have some permutation of the numbers 1 through n. If sigma is equal to tau 1 tau sub k, and sigma is equal to tau sub 1 hat tau sub m hat, where each tau sub I and each tau sub j is a transposition. All right, so what we have our permutation expressed as a product in this way, product of transpositions, and another way as a product of transpositions, right? So each of the taus, tau hat sub, I don't know why I said used a j there, each tau sub I and each tau sub I hat is a transposition. Then k and m have the same parity, which means they're both even or they're both odd. So here is what's unique about a decomposition into a product of transpositions. If you take some permutation, some element Sn, and you write it as a product of transpositions, and then you write it in another way as a product of transpositions, and another, all possible ways that you write it into product of transpositions will have the same parity, which means that they'll always be even, they'll always be an even number, or there will always be an odd number. Okay, so let's prove this theorem, and this is, maybe it doesn't seem that exciting, but this is actually kind of a big deal. So the proof, now the proof is going to rely on a fact from linear algebra. And so what I want to do is take the identity matrix. So let's let I in GL N R be the n by n identity matrix. Now, here's the thing. So you don't need to draw this, but I just kind of want to draw a little diagram here, right? Our matrix, our identity matrix, has, and I guess I should put some ones and zeros on here, right? Our matrix, don't draw this. I'm going to write this out precisely. But our matrix has ones along the diagonal, and then zeros everywhere else. Right? Now, and in particular then, we know that our matrix I, so here's capital I, has row 1 and row 2 and row 3 all the way down to row n. Now, what is sigma? Sigma is a permutation of the numbers 1 through n. And so, sigma tells the number 1 to go somewhere. Sigma tells the number 3 to go somewhere. The number 12 to go somewhere. And so, here's what I'd like to do. Because sigma permutes the numbers 1 through n, we then have an induced permutation of the rows of the identity matrix. So, for example, I just want to do one quick example. Let's say that, that we're working at S4. And so let's say sigma is the permutation 1, 3, 4. Okay, so I'm writing it as a cycle here. So what would sigma do then? So once again, you don't have to write this part down. I'm going to write down the precise sentence in a second. But this particular sigma says, oh, okay, 1 goes to 3, so let's send row 1 to row 3. So we would get a 1, 0, 0, 0 in the third position. 3 goes to 4, so I want row 3 in the fourth position. 4 goes to 1, so I want row 4 there, and then row 2, nothing happens. Right? So this particular sigma would induce the following permutation of the rows of the identity matrix. In general, then, what we have is each sigma permutes or induces a permutation of the rows. So, then sigma induces a permutation of the rows of capital I. And so this result, let me keep going here. So resulting in a matrix, capital A, in GL and R. Now, let's see, what do I want to do? Oh, right. So I'm going to go for a contradiction. So let's just suppose that K is even and M is odd. Right, so suppose K is even and M is odd. So what would this say if we, now sigma is sigma, right? So in the end, no matter what you do, you end up with the same permutation, which means that we will have the same swirling around of the rows. A, whether you use this format or this format, is going to be the same matrix. So using the first decomposition, of sigma, we have, so what would that mean then? Well, each of these taus as a transposition is going to interchange exactly 2 rows. So if we have an even number of transpositions, that would tell us to interchange 2 rows of the identity matrix an even number of times. Each time that you interchange, what happens to the determinant? It gets negated. So if you interchange an even number of rows, so let's write this, if you have an even number of interchanges, then the determinant is going to stay 1. So using the first decomposition of sigma, we have A obtained from I via an even number of row interchanges, And so that tells us that the determinant of A, right? Each time you interchange two rows, you pick up a minus sign on the determinant. So if you do that an even number of times, it's going to be minus one, an even number of times. And so the determinant is equal to 1. However, using the second decomposition, of sigma, we have A obtained from capital I via an odd number of row interchanges and so that tells us then that the determinant of A is equal to -1. That's clearly a contradiction. This is a contradiction. And so what's our conclusion from this, right? Here we suppose that we had different parity. We got a contradiction. That forces us to conclude that either both K and M are even or K and M are odd. So final sentence then would be, therefore, K and M have the same parity. Therefore, K and M have the same parity. That's kind of a nice proof, I think. It uses this fact about matrices, and it says, every time you interchange two rows of a matrix, the determinant changes by a negative sign. And so if you did it by an even number and an odd number, something's going to go wrong. This leads to a definition now. So a permutation sigma in S of n is even if it can be expressed as a product of an even number of transpositions. So if it has a decomposition as an even number of transpositions. And on the other hand, it's odd if it has an odd number of transpositions in its decomposition. So it is odd if it has a decomposition as an odd number of transpositions. And if it has one decomposition that's even, then all of them are even. If it has one decomposition that's odd, then they're all odd. So this is a well-defined definition. So for example, so let's say sigma equals, what do we got here? 1247 times 3457. So how do we decide whether sigma is even or odd? Well, we write it as a product, and we can do it any way we like. Write it as a product of transpositions. And remember the trick that I taught you last time. Here, is a way to write 1, 2, 4, 7 as a product of transpositions. And then here we've got 3, 7, 3, 5, 3, 4. Count them up. 1, 2, 3, 4, 5, 6. That means that sigma is even. Anyway, anybody, you try it. Try it as many times as you like. Express sigma as in any possible way as a product of transpositions. Guaranteed you'll have an even number of them. So sigma is even. Another example, the identity permutation, so I is even. Why is that? Because I can be written as 1, 2, 1, 2. There's a symbol, so I'm going to introduce this notation. So let's let A sub n, it's a subset of S sub n. What I want A sub n to be is the collection of all even permutations within S sub n. So let's let this denote a set of even permutations, right? Because of this previous example, right, the identity is an even permutation. We're guaranteed that A sub n is non-empty, right? So since I is an element of A sub n, we know that A sub n is non-empty. Now you can probably see where I'm going to go with this. I'd like to show that A sub n actually is a subgroup of S sub n. So let's take a couple of even permutations. So given, let's say, call them alpha and beta in A sub n, we have alpha, or let's say it like this, there exist tau 1 up through tau sub k, and tau 1 hat up through tau sub m hat. And these are transpositions. I guess I should have phrased this better. There exist transpositions sorry, I kind of botched that sentence there. So given alpha and beta in A sub n, there exist transpositions tau 1 up through tau k and tau 1 hat up through tau m hat, where k and m are even, such that alpha equals tau 1 up through tau k, and beta equals tau 1 hat dot 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 tau m hat. All right, if you have a couple of even permutations, which is what we just said right here, we took two elements alpha and beta in A sub n. We know that they can be expressed as products of transpositions where in each of these decompositions there are an even number of them. So now, if I look at alpha times beta, that will be tau 1 dot 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 tau k times tau 1 hat dot 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 tau m hat. This is obviously even because k is an even number, m is an even number, so the length right here is k plus m. So now alpha beta is an element of A sub n, and we'll just say in parentheses here, because k plus m is even, And if I look at tau inverse, let's see now, how do you get the inverse? Oh, I'm sorry, I used tau. I meant to use alpha. Alpha inverse, let's see, who would the inverse be? It turns out that the inverse is going to be tau k minus 1, dot, 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 down to tau 1. To find the inverse of alpha, just write these in opposite order. And I'll explain why in just a second. And this is also in a sub n, right? Because k is even. I should say a few words about why alpha inverse can be expressed this way, right? Think about a transposition and what the order of a transposition is. Tau, if tau is a transposition, it means interchange two elements. And then if you do tau again, it means interchange them back, right? So any transposition has order 2, so this is always equal to the identity. So to find the inverse of alpha, just write this expression backwards. If you multiply this times this, notice what will happen. The tau sub k's will cancel, then the tau sub k minus 1's will cancel, and the whole thing will collapse, right? In the end, you'll have tau 1 times tau 1. Those will go away, and you'll have the identity. So what did we just do by the subgroup test? A sub n is a subgroup of S sub n, and it has a special name, right? So it's called the alternating group on n symbols. Right? So the set of even permutations forms a subgroup and therefore a group on its own sitting inside. Now, okay, so we've got A sub n. Let's let B sub n denote the set of odd permutations. So let's let, oh, and I'm going to underline this here. So now let's let B sub n denote the set of odd permutations in S sub n. So we've got another subset of S sub n. Definitely not closed. B sub n is not a subgroup. Right, if you take two odd permutations and multiply them together, what do you get? You get an even permutation. And I need one transposition, so let's let tau in sigma, or sorry, in S sub n be a transposition. Now, the mapping I want to go from A sub n to B sub n. I don't even want to bother giving it a name. There's a function. I'm just going to tell you the formula. The mapping from A sub n to B sub n defined by so if we take sigma, let's call it alpha. In fact, alpha, an even permutation, and send it to alpha times tau. Notice what we get. If alpha is even and we tack on another transposition, we get an odd transposition, an odd permutation. So this mapping right here, right, takes even to odd, and you can check. It's easy to show this is a bijection. It's not a homomorphism or anything like that. In fact, B sub n is not a group. So all I'm really doing is counting. What we get, because we have a bijection, it tells us that A sub n and B sub n as sets have the same cardinality. All right. So since A sub n, no, let's say it like this, S sub n equals the evens together with the odds, and there's no overlap, all right, A sub n intersect B sub n is the empty set, we conclude, let me say one more thing, and the cardinality of A sub n, or the order of A sub n, is equal to the cardinality of B sub n, we conclude that the order of A sub n is exactly half of the order of S sub n. Right? Because S sub n is made up of two sets, two non-overlapping sets that have exactly the same size. And so what we have then, right, we know the order of Sn is n factorial, so the alternating group has order n factorial over 2. We've been studying groups for a while now. I guess this is getting towards the end of week 4. I just want to give you a little bit of a historical perspective now. I guess let's call this foundations of group theory. We've learned enough now, in particular, the alternating group is important for what I'm about to say. So foundations of group theory. It didn't really make sense to bring this up until I introduced this thing called A sub n. So there's really two sources, if you want to point to where group theory got started, there's really two sources. And one of them is, it comes from a long-standing problem, finding the roots of polynomials. So finding the roots of polynomials. Right? People were in search of formulas that would allow you to find the roots of a given polynomial, right? If you've got a degree 2 polynomial, you use the quadratic formula. There's a formula for, this is more complicated, but there's a formula for finding the roots of a degree 3, a degree 4. And so for a long time, people were saying, can we find a general formula? We're stuck, right? I mean, I think it was in the 1600s is when the formula for a degree 4 polynomial was developed. And after that, people were stuck. And so people started wondering, is there even such a formula? And so this goes back to Galois in the 1820s, who showed, and I have to be kind of vague about this, there is no formula for factoring polynomials of degree greater than or equal to 5. And the reason, right, and this is sort of the genius of Galois, was to involve group theory into this question that, for which there's not really, group theory is not, it's not obvious that group theory is involved here. And so it was really Galois' contribution to show that really there's some group theory. In fact, it's about studying symmetry. This problem boils down to studying symmetry. And it turns out, right, remember Sn, that's the symmetric group, right? It helps us study symmetries. It turns out that the reason there is no formula for factoring polynomials of degree 5 has something to do with the structure of A sub n when n is greater than or equal to 5. All right, so I'll just say it like this. This is due to the structure of A sub n, n greater than or equal to 5. This is a long story, and if you happen to go on to Math 483, or 560, whichever version you want to take. Right in the spring, we'll be studying and looking at this question in greater detail. There's a lot of details to go through here, but in the end, it boils down to something weird about a sub n. So there's one of the sources of group theory. All right. The other is more geometric in nature. So this is, I'll say, transformations of space. I mean, space is kind of a hard. That's a weird. Let me say slash geometric objects. All right. So back in the 1800s, people were trying to understand how do you they're studying the symmetries of space, I guess you could say. Right. So I'll say I don't know how to phrase this. I'll just say ... symmetry. They were really trying to get a handle on what it meant for a geometric object to be symmetric. And this really goes back to Riemann. Yes, the same guy that did the Riemann integral, Riemann sums. So Riemann, also a guy named Van Dyck. These guys studying back in the late 1800s, I guess around 1880s. And what they realized as they studied, remember we studied dihedral groups, which allow us to characterize the symmetries of polygons, right? Well, there are more complicated geometric objects out there. So if you sort of generalize this idea, the symmetries of a polygon are captured by the dihedral group. With more general geometric objects, there are, let's say, generalized dihedral groups. So let's say like this, generalized dihedral groups, generalized. And the general theory goes like this, right? To study or to understand a geometric object. If you want to say, I understand the shape of and the behavior of this geometric object, what you should do is you should study its group of symmetries. And so these two, although there are definitely connections, there's some overlap here, these are the two things that led to really an explosion in the study of groups, right, that continues to this day. So that's the end of this chapter. We're going to start a new chapter in the next lecture. And so I guess we'll stop here and see you next time. All right, bye.